We start, Unit 3 was polynomials, looking at the graphs of polynomials and looking at learning how to factor polynomials. And then Unit 4 was all about solving equations and solving inequalities. We did polynomial equations and inequalities. We did absolute value equations and inequalities. And we did square root equations as well. So that's the bulk of Unit 4, is all just solving, and every different type, whether it's an equation or an inequality, they all have their little different things that you got to remember, different little details here and there, the way that you interpret your solution. So we're going to try to quickly review all of this. These are actually the same, if you look at it, the same expression on the left, but this one's less than or equal to 0, and this one is greater, the one on the right is greater than 0, okay? And the one on the left is less than or equal to 0. So that can just make a difference in how you interpret your solution. Do you remember how we solve these? This is why we spent the whole unit before this, which is Unit 3, but the first unit on polynomials, working all this stuff. Yeah, very good. We want to just draw a quick sketch of this. So let's go ahead and do that. And so I want to think about the x-intercepts and their order. So this x-intercept is 5 over 3. This x-intercept is -1. And this x-intercept is -1 over 3. So I obviously have to graph them properly. So there's -1. There's -1/3. And there's 5/3. It doesn't really have to be to scale for this, but it might help. And in order to graph, which we didn't review one of these, right? So here's our quick review. Now, if you were asked to sketch this or graph this on the exam, it would require more details, and I'll talk about that in a minute. But what do we have to think about? Probably one of the first things we're going to think about the degree. So this is degree 2, plus 3 is 5, plus another 1 is degree 6. So degree 6, we care that it's even. So it's an even degree polynomial. And then we look, and if you recall, if it has a factor that's 1 minus x, that's going to change the sign of the a value because it would have to be factored. Okay, so watch for that. Whenever it's 1, we do a lot of work with x minus 1 type factors. And then once in a while we throw in a 1 minus x or 2 minus x or whatever. You understand what I mean? And it changes the question, whether it's absolute value, whether it's polynomial, whether it's logarithms that we did more recently, like it changes them no matter what. So just watch for that throughout the whole exam would be my recommendation. But this one's simple. It doesn't have any of those. That means our a value is positive. I take this, the fact that it's even degree and the a value is positive, I put those together, and that gives me the end behavior of the function. So both ends are pointing up. Okay? What's going on here? My first factor here that I'm going to come from the left is order 3, so that's a cubic twist. Now in this case, doesn't really matter that it's a cubic twist. It wouldn't change the solution, but you should probably draw it accurately. Then I have a turning point, so that one definitely matters. Then I have a straight pass through. If you were sketching this, you would 100% have to label everything, do what I did so far, but then you would also have to determine and label the y-intercept. Intercepts are pretty much always something we've been able to calculate through this entire course, whether it was, no matter what kind, not in trigonometry we could, but we didn't. But in every other kind of function we explored, we looked for the intercepts, both x and y. So keep that in mind too, that if you're ever asked to sketch or graph, intercepts are an important part of that, except for trig. Okay, so now we got it, and now we just use this graph to read our solution right off of it. So this is, this is, here we go, less than or equal to 0. Where is this less than or equal to 0? In this little bit here, and in this bit here, and it is equal to 0 right there. It's also equal to 0 right there. So that means my solution ends up being from -1, including -1, all the way to 5/3, including 5/3. It includes this point because it's less than or equal to. And I'm actually going to go over all the different types of solutions you might have. What if it was just less than? Then it's still less than here, and it's still less than here, but you don't count that point because it's equal to, and we don't count that. So I would have to say, therefore, when x is, I would have to go -1 less than, and not less than or equal to, just less than x less than -1/3, and -1/3 less than x less than 5/3. So just the difference in the symbol in the question makes a difference there. And part B says greater than, not greater than or equal to, greater than. Where is it greater than? Just down here, below -1, and just up here above 5/3. Now, some people at the time, and by now we've done so much more work with graphs and stuff and intervals that hopefully you've overcome this. But I remember back in the time, some people do have a problem with like this is less than -1, but it's technically on the page above -1, like the y values are going up, but this is for x values less than -1. You know what I mean? And that has to do with reading on the domain for different y values. And it turns out that's kind of a big thing in mathematics, but it's a little bit strange at first. So anyway, for this one, it's going to be x just less than -1 and x just greater than 5/3 is where it's greater than or equal to 0. Remember, stop me if you have questions. Otherwise, I'm going to go fairly quickly. What if it's greater than or equal to 0? It certainly changes things. So I would still get here, but except it would be x less than or equal to -1. And I would still get this, except it would be x greater than or equal to 5/3. But there would be one more that you have to put in.
X is equal to -1.
Good. That point where, yes, it does not cross and go above, but it does become equal to at that point. And those are the tricky details that we're looking for in the interpretation of the solution. Okay, next question. This is actually supposed to be just -24. First one starts off easy. What do you notice?
X factor.
There's a common factor of x. That makes things easy. If there's a common factor in the coefficients, you take that out too. Man, if you missed that, if there was one of these on the exam or a test or anything like that and you missed that, that would be really unfortunate because it does make your life so much easier, right? Takes it down a whole degree. And here's what happens in some cases. So what's left here, I'm going to check with the discriminant. And that's not a perfect square, but it's positive, so it's solvable, but not factorable, so we're going to use the quadratic formula. And so then people do this, so x equals -b plus or minus the square root of b squared minus 4ac over 2a. What have I missed, though? Yeah, and that's an easy one to just forget, right? So write it out at that. That's where I would write it out at that step. Now, depending on this is going to be a quick review, but depending on the instructions, what if it said exact value? Then you'd have to reduce and fully reduce. You'd have to reduce this 880. I think it's obvious that it's divisible by 4. So do that. But another thing that you could try is multiples of 4. So what other perfect squares are multiples of 4? 880, hold on, divided by 4 is 220. That's also divisible by 4. So I could go back to 880 and divide it by 16. That gives me 55. And my point here is you got two ways that you can do this. When you do this division, so 888 divided by 16 is 55. It's got to be a perfect square, right? There's no perfect square that goes into 55, so you know you're good. If there's a perfect square that goes into 55, it means you didn't pull the biggest one out that you could, so I would go back and I would go further. You're probably not going to get a big, huge number. That's hard to produce in this case on an exam. We got 55, one step left here. I can divide the 20 and the 4 and the 10, divide them all by 2. So x equals 0. Don't forget that one. Negative 10 plus 2 root 55 over 5, and negative 10 minus 2 root 55 over 5. And I'm sure you can punch that into your calculator proficiently if required, if you're asked for 2 decimal places or something like that. Yes?
So these are the questions where you use synthetic division, right?
You might if you have to, yeah. I think we're going to see that in the next example. So. Okay. Simple one, but don't forget quadratic formula. Don't forget discriminant. Next one does not have an x factor in it, which means it's factor theorem. Factor theorem says that we have to go hunting for a factor. And remember, in unit 3, the first unit on polynomials, we were just factoring. And we were often factoring something that was like f at x equals this thing. And if it wasn't there, we'd say let f at x equals this. But in unit 4, we didn't do that. We streamlined the process because we got good at it. That was for learning purposes. That was for other reasons that we were doing that in the first unit. And then we dropped that for the second unit. So if you're solving like this, you don't have to do something, but but it is still factor theorem, right? And therefore, Oh, if f at something equals 0, then so-and-so is a factor and you go on, okay? When I start hunting for factors, I know they have to be factors of 12, 1, 2, 3, 4, 6, and 12, positive and negative. I'm going to look at the ones first, and you can do the ones by looking at the coefficients. None of the combinations of these coefficients add to 0. I just do a quick glance. I don't spend a lot of time on that. If you're good at doing that kind of stuff, it should be obvious. Otherwise, you move right on. And it turns out f at 2, well, there is no f, but 2 works, yes?
Don't we also have to check 1/2 and negative?
We never made you do that, though. You're right. There are some other ones that you could do. 3/2 could be one as well. Like, there are other possibilities, but we will always give you integer values that you could find. You don't have to go looking for rational values. So it turns out 2 works. If you punch in 2, you should get 0, which means x minus 2 is a factor. So I start with x minus 2. And this is where you would use synthetic. But I'm going to show you that trick again. Put your pencil down and watch. Now, I don't suggest that if you didn't learn this before that you start using it now. Not very many people, I seem to remember, were using this. Some years people like it. Some years people don't. I do know that this is going to be a quadratic trinomial. It might have a coefficient of 0, but it's going to be a quadratic result. So 3 terms. So the first term, this thing times this thing has to give me that thing. So it has to be 2x squared. 2x squared times x is 2x cubed. This is going to be my constant. So this times this will give me 12. So that's got to be negative 6. So then all you have to do is figure out the middle term. And that requires a bit more work. This is the part that's a bit harder. But remember I talked about efficiencies. If you're good at this, it's still even faster than synthetic. But it's up to you. Don't don't waste your time struggling through this. Synthetic is still quite quick. Okay. But in this case, I'm looking for something that's going to give me the 4x. So what I'm going to do is I'm going to do x times negative 6 gives me negative 6x. Don't write this down yet. And then negative 2 times something has to give me something to give me the negative 4x in the middle, which means this has to be 2x. 2x minus 6x is negative 4x, which means this has to be negative x. Negative 2 times negative x gives me negative 2x minus 6x is negative 4x. It takes a bit of practice, but it is a little bit faster. Otherwise, you're doing synthetic, so let's do that. So you've got x minus 2. I'm going to move it over a little bit. 2, negative 5, negative 4, and 12. Bring the 2 down. 2 times negative 2 is negative 4. Negative 5 minus negative 4 is negative 1. There's that negative 1, so we were right. That's positive 2. Negative 4 minus 2 is negative 6. Negative 6 times negative 2 is 12. Subtract to 0, which better happen, and you're good. And that is factorable. You can check the discriminant. And take a look. I've got two terms that are the same. That's a reminder that that can happen. If I was graphing this, I would pretty much have to write it like that to recognize that it's an order 2x intercept and it's got a turning point. I wouldn't write it like this. I would write it like this. If it's an equation, you don't have to rewrite it in a step, but you should realize that there are only two solutions. There's a, look at that, 3 over 2. Negative 3 over 2 would have been one of them, right? Don't write the same solution twice. That just kind of shows you're not paying attention, I guess. So that's all the work on polynomials, inequalities, and equations. Factoring, factor theorem, all the different kinds. You got to know all that. We did them with difference of cubes, sums of cubes, all of that as well, which we reviewed last day. Now we get into absolute value equations and inequalities. We did absolute value equations. Really simple ones aren't very interesting, like this. 2x minus 3 equals 5. That's not very interesting. We did these on the first day because we were learning about that strange behavior of the absolute value function, how it behaves algebraically. A little bit more interesting when you have something like equals x plus 7. You have to consider cases. This is similar to the one we're going to do next. It's not identical, but it's similar, so we'll get to that. So if it's a single absolute value equation, you kind of do it one way, and you have to interpret your solutions. If it's a double absolute value like this, you do it another way. And if it's a single absolute value but inequality, again, there's a little bit more to the interpretation. So this is what I'm talking about, all these different little types. How do we do a double absolute value equation? I look at the two absolute value, the factors inside the absolute value signs, and I get x plus 2 and x minus 4, and I write them down on the side like that. And I do a number line. And I think of these as factors. What would make this factor 0 if I put in negative 2? So that's the place that I mark. And positive 4. And I pick some value that represents each of these intervals, and this is going to come up again in the rational functions unit next. Some value that represents this interval. Any value less than negative 2 would work, so I always use negative 10. Negative 10 plus 2 is negative. Negative 10 minus 4 is negative. I just write that down. Some value in this middle interval would be what? 0, thank you. I'm going to write them down. I use negative 10 here. I use 0 here, just in case. you're wondering where these negatives came from. 0 is a nice one. You can't always use 0 in the middle interval, but when you can, it's nice to use. 0 plus 2 is positive. 0 minus 4 is negative. And then any number that's bigger than 4, but let's use 10. And 10 plus 2 is positive, and 10 minus 4 is still positive. This is what I'm talking about. Very often we did these, and it was like the ones on the left are negative, the ones on the right are positive, and the ones in the middle switch. One's positive, one's negative. But it's not always like that. Again, if you have like a 2 minus x factor, it changes things. That guy always sneaks in there when it's a something minus x, and it changes up the patterns. And if you're relying too much on the patterns that come up in the kinds of questions we look at and not really thinking and understanding, that's when you get yourself into problems, right? So this is x less than or equal to negative 2. This is negative 2 less than or equal to x less than or equal to 4. And this is x greater than or equal to 4. And the whole point of this process is because algebraically, what the absolute value function is doing is it's asking the strange if this then that question. And if you've taken computer programming, you're familiar with this. You're good with that. But if you haven't, it's a little bit harder, right? But it's saying if this is a negative, multiply by negative 1. If it's not negative, leave it alone and don't touch it. That's what absolute value does. So in this interval, this factor, this binomial, is negative always for every value in this interval. What does absolute value do when something's negative? Multiplies it by a negative. So I go back to this. I'm rewriting this by getting negative x plus 2. X minus 4 is also negative, so I multiply this by a negative. Don't forget your brackets. Equals 8. 8 doesn't get multiplied by negative. It's not an absolute value, right? Leave it alone. And then I solve. And in the middle one, well, x plus 2 is positive for all values in between negative 2 and 4. So I leave it alone. So I just write x plus 2. But x minus 4 is negative. So absolute value says multiply it by a negative. That's why we do what we do. And then both of these are positive, so I leave them both alone. If it's negative in your case checks up here, you multiply it by negative in brackets. That's right. Okay, now I'm going to solve. These are easy, so I'm going to solve them quickly. So I get negative x minus 2 minus x plus 4. Negative 2x equals 6. X equals negative 3. X minus x is 0. 4 minus negative 4 is 6. So here I get 6 equals 8. And then I get 2x, and I'm going to add 2 to both sides equals 10. X equals 5. Now what I do is I take these solutions and I check them against the interval that they are in. They might match, they might not match. Is negative 3 less than negative 2, less than or equal to negative 2? Yes, so we're good. Is 5 greater than or equal to 4? Yes, so it's fine. 6 does not equal 8. Never true. So there's no solutions there. No solutions come out of that middle part. Therefore, x equals negative 3 and 5. That one's relatively easy to interpret the solution. You're just checking each individual part to see if it's in the domain of the case that it came from. Yes, Isaac. The other thing you can do is you can skip all of that checking in the interval, and you can take that solution and check it left side, right side in the original equation. That works too. If you can do a quick left side, right side check in your head or on your calculator, that might be just as good. Doing absolute values on your calculator is a little wonky. I don't think they don't usually have an absolute value function. But if you can do it in your head, you might be fine doing it like that. So you can do left side, right side checks as well. You'll get left side equals -8, right side equals 8, or something like, in that case you might not, but often something like that happens, okay? Okay, this one is the absolute value inequality. We did not do double absolute value inequalities. We just did single absolute value inequalities. So this one's a lot like if this was just an equation, an equality, this equals this, it would be similar until the very end. The interpretation of the solution is different. So I split it up by cases. Oh, here's a mistake some people make. They go like this, 2x plus 2, 3x minus 1. They do this. Why is that wrong? Tyler? Yeah, this isn't an absolute value. I don't have to think about cases for that. It just is what it is. So I only have 2 cases, and they come from the absolute value. So it's when 2x plus 2 is less than 0, or less than or equal to, whichever one you like. And when 2x plus 2 is greater than or equal to 0. Those are my 2 cases. Think about it. When this expression is less than 0, absolute value says multiply it by a -1. When the expression is greater than 0, absolute value says leave it alone. But the other part to this is I need to know when those cases occur, when in the domain. So I have to solve these. To figure out when these cases occur for what values of x. That's where my check comes from. So when it's less than 0, I multiply it by a negative. And when it's greater than 0, I leave it alone. Then I just go and solve each of these. I'm going to solve them in slightly different ways. I know you're busy writing, but make sure you're watching as well. Yep.
Can't the right one still be less than 0? And if it's greater than -1?
Yeah.
Wouldn't that?
Nothing wrong with that. And for these ones. Yep. Yep. Okay, so I'm going to subtract 3 from both sides and add 2 to both sides. So I get -5x less than or equal to 1. So x. What do I have to do when I divide by a negative or multiply by a negative? Flip the sign, right? So x is greater than or equal to -1/5. By the way, eyes up, pay attention quickly. This sign comes from here, has nothing to do with that. Absolutely nothing, or that, or that, or that. This has to do with the case of this being less than 0, so I do the negative. This has to do with that. Okay, for the other one, I'm going to do this one a little bit differently. This is not the way I would recommend doing it, but if you end up, but I want to point it out and talk about why. And if you end up doing this way, there's a little thing that you have to think of. In this case, you might move the 2x over to keep everything positive. So I'm going to add 1 to this side. Subtract 2x, and I get this. But this is a really difficult way to read and understand what it's saying. So then you might flip it. And if you did this, then you've made a mistake. You can't change sides without flipping the sign. If you're not doing any operation like multiplying by a negative or anything, the big side should be pointing to the same thing. So watch for that. We didn't do a lot of that. Now, everybody good? Any questions? Now, how do we interpret this solution? Well, there's a couple ways you could do it. In this case, doing it as single number lines would work. Sometimes we do it as a full number line. So I'm going to do it as a full number line. It's going to be fine this time. I got to find all these positions. I got to find -1. I got to find -1/5. It's going to be over here. And 3. And I ask myself, what kinds of numbers are less than -1, that would be here, and greater than 1/5, that would be here. Well, there's no numbers, there's no overlap. So this side, this case has no solutions because there's no numbers that are less than -1 and greater than -1/5. What numbers are greater than -1 and greater than 3? Anything greater than 3. But if it's greater than -1 down here, it's not also greater than 3. It has to satisfy both. So my solution is therefore x greater than or equal to 3. Again, you could check this. You could take this solution, sub it in, and see what you get. Left side, right side. That can work as well. Although since it's an inequality, it won't give you a full solution, but it might help check to make sure you're on the right track at least. What do you think? Interpretation of those solutions was a big part of that. Yeah.
So because the first case didn't work, do you want us to exit it?
In that case, we usually just write a final solution. It would be a good idea to yourself maybe to write no solution or an X or something like that. Would be a fine thing to make a note just to yourself even. Take a look up here. We're going to do 2 questions. This one's an equation and this one is an inequality. And they are done very differently. You may have noticed if you were looking carefully at the solutions for this course throughout when we were doing this unit that some of the solutions actually do them this similar way. So another teacher does it that way to keep things consistent. I do it, and some of the other teachers do it differently to remind us that equations are different from inequalities. So, I mean, it's up to you. You can do it whatever way you want. But what you absolutely have to remember is they're very different questions. And the way that we solve an equation, you cannot do an inequality like that. First thing I'm going to do is I'm going to notice that this thing is factorable. It's going to kind of help us actually. Because I noticed something. Now off to the side, we need to multiply by something to clear all of the denominators. So you might multiply by every denominator. But that would be overkill. Because if you were doing a question like this, 1 over 3 plus 3 over 4 minus 1 over 12 equals 0. To clear those denominators, you could multiply by 3 and 4 and 12. But multiplying by 12 will cancel both of those. So 12 would make it easier because your numbers are all smaller. And that's the same thing that's happening here. I don't need to include that one because multiplying by both of these, as you can see when it's factored, will clear everything. It's going to have to be factored anyway. So, or at least for often factoring is the kind of thing we have to do anyway. So doing that as a step might be useful. But if you just notice that these are the factors of that, then don't multiply by more than you need to. So I'm going to multiply everything by x and x plus 3. And I'm going to write the whole thing out. You don't have to. And this is an equation. I'm not multiplying it by something over itself. Not multiplying by 1. I'm multiplying the left side and the right side by the same thing. Right? When it's an equation, we do it that way to keep everything balanced. So I can see that these are going to divide to 1. This divides to 1 with that. That divides to 1 with that. And this is probably the line that you would jump to, again, for efficiency. And for equations, we can do this. It makes our life so much easier. We can just multiply to clear the denominators. Things will cancel out. I got 7/9. Then we look at an inequality, and it's so different the way we have to do these. Why is it different? Because with an inequality, when you multiply or divide by a negative, you got to flip the sign. And there are cases when each of these is negative and when it's not. So you'd have to split it up into cases, kind of like the absolute value, but it ends up, there's an easier way of doing it. And you could have more than 2 factors. And if you have more than 2 factors, you'd have more than 3 cases. You'd have a lot of cases, and it'd be a lot of work to break it up in all those cases. It'd be really confusing. So the cases way wouldn't be a good way of doing it for this. The best way of doing it is the way we're going to do it right now. And that's by getting a common denominator, bringing everything to one side, and making the other side 0. So again, if I notice that I can factor on the left, and I'm going to bring the right side over. And I notice that they both already have an x plus 3. So I just need this part. Uh-oh. No, undo mistake. Oh. Okay, there we go. Oh, this isn't going to work for me, is it? There we go. I just need to add an x minus 3 to this, and this is where we do times it by x minus 3 over x minus 3. That's what I was trying to squeeze in there. X squared minus 4 less than or equal to 0. So now I get x squared minus 4 minus x squared plus 3 over x plus 3, x minus 3. And then on top, this works out nicely because it's x squared minus x squared makes our life a little bit easier. And I end up with, that's just gone. Oh, this should be 3x. That's just gone. So I get 3x minus 4 over x plus 3, x minus 3.
Can we, from the first up to the second, can we just put it all in one?
Absolutely.
No.
Yeah, for sure. This would all be, all 3 of these steps would be like sort of one step and then you get to there kind of thing, or at most 2 steps. I don't know how helpful this is, but this is just one of those questions where I've noticed that if you make a tiny mistake like dropping a negative somewhere in this process, it can drastically change the question. So this is kind of an unuseful tip. Try not to make any mistakes. You're like, thanks, Mr. Belair. Isn't that kind of always the point in every question? Try not to make mistakes. I know. But for this one, I don't know if it requires you to go even more slower. Just be mindful of the fact that dropping a negative can drastically, it might not, but it might, because you might change something that was supposed to be factorable into something that's not factorable or something like that. It can make a major difference in how the end works out. If you ended up with a quadratic on top? Like, what are we about to do next? We have to find the x-intercepts and the vertical asymptotes. If you had a quadratic on top that wasn't factorable, you would be doing the quadratic formula to figure out what the x-intercepts are instead of just going, you know what I mean? Like, so just, I don't know, from my experience, I guess be aware that this is one of those questions that can really get you. So we're not doing a full sketch here, but we are using our understanding of rational functions. Oh, I want to go back and look at something. And when they are above 0 and when they are below 0. So I'm going to go way back to the rational, this one. Nope, this one. Let's take a look at this graph. So right here, the graph is positive. Crosses an asymptote. Now it's negative. Crosses an x-intercept. Now it's positive. Crosses an asymptote. Now it's negative. And it stays negative. Oh, sorry. It's still negative. What I meant to say was crosses an x-intercept, goes positive, and stays positive forever after that. We know the behaviors of an asymptote. It'll approach that asymptote closer and closer and closer forever. It will not curve back down or something like that. That's not what asymptotes do. When it gets out to this part of the graph, it goes on and on and on and on forever. So it will always be positive because there's not going to be any more asymptotes or x-intercepts. So for rational functions, the only place a graph switches from negative to positive or positive to negative is at an x-intercept or an asymptote or a hole, but that almost never happens. Okay? So we need to find the x-intercepts and the asymptotes and do testing to see where it's positive and where it's negative. It doesn't always change. It doesn't always change, so you do have to check. Okay? It doesn't just flip back and forth. It tends to, but it doesn't always. Okay? So we're not doing a full sketch here, but we're using our understanding of these functions to figure out where it might change from positive to negative and vice versa. So what are my x-intercepts? That is when the numerator is 0. So my x-intercept is when 3x minus 4 is 0. You don't have to write all this out. So when x is 4 over 3. What about vertical asymptotes? That's when the denominator equals 0. So that's when x plus 3 is 0 or x minus 3 is 0. So x equals plus and minus 3. And this is what I mean by if you messed up and you had the wrong numerator, it can drastically change how easy or hard the next part is. Now I do a number line. And I mark these points -3, 4/3 is just a bit more than 1, and +3. And I start doing checks again for values that represent those intervals. Yes?
Are we supposed to distinguish between the...
Yes, very good. And it's useful when it's an asymptote to show that, which will come up momentarily as part of our interpretation of our solution. This goes back to what I was talking about. Think about that asymptotic behavior. Once it goes above 0 and it's approaching the asymptote, it's never going to turn back down. And same thing over here. It's positive, or actually I don't know what, but the graph we were looking at was positive. It's going to stay positive forever. So whatever happens here will stay happening here. So any value in this interval can represent the interval. We use -10 and we're just checking it in here. So if I use -10, this is -30 minus 4, that's negative. -10 minus 3 is negative. negative 10 plus 3, sorry, is negative. Negative 10 minus 3 is negative. So I got 3 negatives. So this one is negative. What's a good value to represent this interval? I would say 0. Yeah, good, 0. Because it changes from negative to positive. 0 minus 4 is still negative. 0 plus 3 is positive now. 0 minus 3 is negative. 2 negatives means this part's positive. What's a value between 4/3 and 3? This is one of those things that you've got to actually think about. What 4/3? What value is that actually? And pick a number between it and 3. 2. Thank you. Right? So pick 2. 3 times 2 minus 4 is 6 minus 4, which is positive. 2 plus 3 is positive. 2 minus 3 is negative. I got 1 negative. That's negative. Pick a big number like 10 and positive, positive. 10 minus 3 becomes positive. This one flips back and forth. It doesn't always. It often does, but not always. This question is asking when is this function, when is this expression less than or equal to 0? When it's negative, which is these two intervals. And it's less than or equal to, it's not equal to at an asymptote. So x less than negative 3 is that interval. And this interval is negative 4/3. Include that point because it's an intercept, so it is equal to 0 at that point. It's not equal to 0 because graphs do not exist, or expressions do not exist at their asymptotes. Questions? You look back at this course and you realize why it's called a functions course. It's all about understanding functions. So much of even solving algebraically has to do with the properties of the function, what we know about functions. Like, isn't that interesting? And this goes all the way back to grade 9. We just didn't know it back then. We didn't know that the algebra that we were doing was related to the graphing. Yeah. Yeah. Sure. Okay, let's do this quickly. We only have 10 minutes. It's going to be hard to get through, but I'd like to try to get through the whole thing. First thing is we want this factored. I'll factor it for us. It's nice. We're going to need it anyway, so it's nice to do it at the beginning. It's also good for looking for holes. No holes in this one. Oh, the difference between horizontal asymptotes and oblique asymptotes is important for when you get to that part. How you know whether it's oblique or not. We'll talk about that a bit more tomorrow. This one's not oblique because the degrees are equal. Okay, equal degrees means it's not oblique. So that means it's a horizontal asymptote. It's one or the other. We have to do intercepts, asymptotes, and the end behaviors around the asymptotes in order to sketch this. So first of all, I'm going to do intercepts. The y-intercept is when x equals 0. I'm going to use the first version, 0 squared minus 4 times 0 plus 3, 0 squared minus 4, which is negative 3 over 4. The fact that that's negative is going to be really important. If it turned out to be positive, I wouldn't be able to draw it. I'd be like, what's going on here? This isn't making any sense. Something as simple as missing the negative here will stop you drawing your graph in your last step. So watch again for those little things. When y equals 0 is when the numerator is 0 again, kind of like the last one. So it's when x minus 3 is 0, or when x minus 1 is 0. So my x-intercepts are 3 and 1. Positive 3 and positive 1. Asymptotes. Asymptotes occur when, vertical asymptotes, as we just talked about, occur when the denominator is 0. So when x plus 2 or x minus 2. So my asymptotes are x equals plus minus 2. I'm going to start with the one on the left, which is x minus 2. Everybody look at me. What happens around a vertical asymptote? The function gets really, really, really close to it, approaching from the left or from the right, and gets really, really, really big or really, really small. And all these different combinations, they both go up, they both go down, or they trade directions or whatever. But I'm getting really, really close. So what is my test? Like, if you're not visualizing this when you're coming up with your test, I don't know what you're doing or why you're trying to shoot yourself in the foot. Visualize the behavior around these asymptotes. Okay, so I'm picking values that are x equals -2, that are really close to -2, and I'm going to start on the left. What would that be like? -2.01. And just to the right is -1.99. And I'm going to go to the factored form. So if I'm doing -2.01, I'm just writing that down because we can't see it. -2.01 minus 3 is negative. Minus 1 is negative. Minus 2 is negative. -2.01 plus 2, still negative. -2.01 is a bit bigger than 2. So it's still negative. So that's 4 negatives, which means this is positive. If I do -1.99, minus 3 still negative, minus 1 still negative, minus 2 still negative, but -1.99 plus 2 is now positive. So now I have 3 negatives and a positive. That's a lot faster, more efficient than punching it into your calculator. But if you can program your calculator and do it that way, that's fine too. And if you do it that way, you could check more than one value. You could check -2.01 and -2.001 if you really want to make sure that that the asymptote's there.
Are you sure it's the proper way to write it, like as x?
Yes, we're about to do that. Then, exactly right, we summarize. This is saying as x approaches -2 from the left, y is going to positive infinity. And as x approaches -2 from the right, y goes to negative infinity. Now we do positive 2. So 1.99 minus 3 is negative. 1.99 minus 1 is positive. 1.99 minus 2 is negative. 1.99 plus 2 is positive. So this one should be 2 negatives and makes a positive. And 2.01, when you do the same thing, makes a negative. So this means as x approaches positive 2 from the left, y goes to positive infinity. As x approaches positive 2 from the right, y goes to negative infinity. We got 4 minutes to do horizontal asymptotes. My horizontal asymptotes occurs. These have equal degree, x squared over x squared, so you look at the coefficients. If the degree on the bottom is bigger, your horizontal asymptote is y equals 0. If they're equal, you look at the coefficients, it's 1 over 1. So where did I do this? Here we go. This was vertical asymptote. Here's horizontal asymptote. It's y equals 1 over 1, so y equals 1. Picture your horizontal asymptotes. A rational function does this. In the middle, it goes up, it goes down, it's turning maybe, it's going up, it's coming down, it's approaching other asymptotes vertically, doing all this kind of stuff, and then it smooths out and settles down as it goes out into the far reaches of the x values. That's where horizontal asymptotes occur. Graphs can cross horizontal asymptotes. They never cross vertical asymptotes. They can cross horizontal asymptotes, but not when they get out far ends. So I am checking f at -100 and f at +100. And in this case, you actually have to plug it in. and actually check the values. It doesn't matter if it's positive or negative. Of course they're both going to be positive. The asymptote is 1. It's approaching that. They're both going to be close to 1. So this is 1.04 and this is 0.96. So this is as x goes to negative infinity, y approaches 1 from above. And this is as x goes to positive infinity, y approaches 1 from below. I am comparing the value to whether it's above or below the asymptote. 0.96 is less than 1. So it's below the asymptote. So after you have all the work done, intercepts, asymptotes, in this case it was vertical asymptotes and horizontal asymptotes, you've done all the testing, all the calculations, everything like that. Then we put it all together and all the pieces must fit. So let's take a look at what that looks like.
So this doesn't count as accurate graph.
This is a sketch, that's correct. To me, I don't think these are formal definitions, but to me, a sketch means like not on a grid, and there's not a formal scale, not an accurate scale. We don't know all the points. We label the things we do know, whereas a graph is with graph paper with a grid and a scale and that kind of thing.
So I know you said before that we can't just say above and below. Which one is that for? Is that for when we do S at negative?
Yeah, I like when you have either horizontal asymptotes that you do this statement as well as state above and below. For yourself, it's a good idea to state that, but I like having this written out as well. Okay, so first I'm going to mark everything on the graph, which is things like asymptotes and x and y intercepts. So in this case, we have asymptotes at positive 2 and negative 2, vertical asymptotes. You should use a ruler for your asymptotes. Okay, and then let's focus here, folks. And then we want our horizontal asymptote, which is at y equals 1. And then we're going to label them. So this is x equals 2. You have to label your asymptotes always. X equals negative 2, y equals 1. I'm going to put in my x-intercepts are positive 1 and positive 3. And negative 3 over 4, and remember when I said when you're calculating the y-intercept, if you just do the little thing of missing the negative, which in this case it's in the denominator and it might be easy to miss, right? I could see somebody missing that. And if you miss that and then you went to graph it, the pieces wouldn't fit and something wouldn't make sense. Next, if you get all that done and you want to watch, that might not be a bad idea. I'm going to pencil in all of the little details of the end behavior, and then I'm going to make sure that they fit. So this one, it says, as x approaches negative 2 from the left, we go to positive infinity, so we're going up. As x approaches negative 2 from the right, we're going down. So negative 2 from the left, we're going up. Negative 2 from the right, we're going down. As I approach positive 2 from the left, I'm going up to positive infinity. Positive 2 from the right, I'm going down because it's negative infinity. So from the left, I'm going up. And from the right, I'm going down. And I'm just putting faint little pencil marks that you can then either erase later or just go over when you need to. I'm not necessarily actually going to use them. I'm just indicating to myself. And then the last part here, where's my horizontal asymptote? Here they are. As I go to the left, as x gets really big and negative, I'm approaching from above. So that's right here. And as x gets big positive, I'm approaching from below. So that's here. And like I said, all these pieces have to fit. So now I'm going to go start connecting them together. And if something doesn't fit, you've made some kind of mistake. And you have to go back and figure out what it is. Something's out of place. Look at how all these parts fit together. This has to come from here, cross through there, and then join up with that. If that negative 3 over 4 was up here, I wouldn't be able to do it, and you would do something like this. If I put the negative 3 over 4 up here, somebody would do this. How do I know that's wrong? Yeah, these are what I might call phantom x-intercepts. You didn't calculate them, but you drew them to make it work. That is not possible. That doesn't happen. Okay? So if you're crossing the x-axis with a line where there isn't an x-intercept, you've done something wrong. And then this one joins from here, crosses the x-axis, and then goes out along the asymptote. And if there weren't an x-intercept there, this wouldn't make any sense. So either you missed an x-intercept or something is wrong. Something's out of place. A graph could come down here, turn without crossing the x-axis, and approach from below. So maybe you only have one little thing wrong. I don't know. Okay? And that's our final sketch. All right, here's our next one. Oops. First one was given in expanded form. This one's given in factored form. If we're really nice, we give it to you in both forms. So you can't make a mistake factoring or a mistake expanding. And you'll need both forms. Might not be obvious right away that you need both forms, but you'll see for this question later on that you do. There's one thing that is just easier to have both forms. There's another reason why you need it. What do you notice? What jumps out at this one? Very good. So we've got the same factor on the top and the bottom. Means a whole at x equals -7. Then what we want to do is rewrite this. Because that's the function we're actually going to graph. Okay, and then we're just going to include the whole. I'm going to add this little statement, let y equal f at x, so I can use function notation throughout my solution. And like I said, I'm going to expand this. So I've got an x plus 1 and an x minus 1, so on top that's x squared minus 1. And I'm going to expand the bottom. I don't need that bracket. And then I am going to expand the top fully as well. So that's x cubed minus 5x squared minus x plus 5. Now I'm going to go ahead and do the intercepts. Some of this I'm really going to whip through today. Again, stop me if you have questions, but it's same as what we did in the last example, so it's not, I don't think it's worth going over. So the y-intercept is when x equals 0, but in other words, it's just the constants in the top and the bottom. So it's going to be 5 over 6. And the x-intercepts are when y is 0, which I'm going to take when the numerator up here is 0. So it's plus minus 1 and positive 5. So I've got 3 x-intercepts. And only 1 y-intercept. How strange. Next, we're going to do vertical asymptotes. Asymptotes, and start with vertical asymptotes. Vertical asymptotes occur when the denominator is 0. Again, looking at factored form, it's when x is negative 3 and negative 2. And I'm going to start from the left with x equals negative 3. And remember, this is part of what we did, so I'm just going to kind of write down the properties, but if you have any questions, you can stop me. We pick values that are really close. I told you yesterday to visualize getting close to it and thinking about what the graph is doing. So we pick values that are very close to the left and close to the right of negative 3. And I just determine if it's positive or negative. I'll do this once. So for negative 3.01, oh, there's a lot to do here. Negative, 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 negative. They're all negative. So 5 negatives means this should work out to be negative. This one works out to be positive. So as x approaches negative 3 from the left, y is going down to negative infinity. And as x approaches negative 3 from the right, y goes to positive infinity. Just one. So this one turns out is positive and then negative. Negative 2 from the left. As x approaches negative 2 from the right, y goes to negative infinity. Yep.
On the exam, are all the questions going to be marked the same amount of marks? So like usually on the test we did.
Very similar to the way the unit tests were. Not always identical, but similar, yeah. You might think, oh, this is the same question from the test and it's worth a different amount of marks. But sometimes little quirks in it make a difference, like if it's factorable or not. So, but generally speaking, yes. Yeah. Okay, and then finally, what we're really looking forward to seeing here is the oblique asymptote. Oh, this is what we didn't talk about. I forgot. We didn't make note that it has an oblique asymptote because you can see it down here in this line. It's degree 3 over degree 2. And I think I said in the last example why, like there's a trick to remembering this. When we go to find the oblique asymptote, we actually do this division. This top divided by this bottom. If they were flipped, you wouldn't be able to do the division. Right? Polynomial division only works a higher degree divided by a lower degree. So when you have that situation is when you can divide. That's when you do divide because you have an oblique asymptote. So, or you just memorize when the degree on top is exactly 1 more, is when we have the oblique asymptote. So the first thing we're going to do is we're going to find the asymptote. And this is why we needed the expanded version, and we can't do synthetic. Synthetic only works for a linear term, degree 1 term that you're dividing by. So we have to do polynomial long division. Yeah.
So if it's the same, it's a horizontal asymptote.
That's correct. And that's the example that we saw previously.
Yeah, so
If it's one less, it's still horizontal, and the horizontal asymptote is at 0. Yeah. All right, plus 5. Who remembers how to do polynomial long division? Some of you do. Oh, not too many. Some. Okay, good. Few of you. So what I do is I ask myself, how many times is x squared going to x cubed? But really what I'm asking is what thing times x squared gives me x cubed? That's an easy way of asking, and the answer is x. And I'm going to line it up over top of the x term. So that when I do x times x squared, and I write it here, when I subtract, because that's what I'm going to do, these have to give you a 0. So then I multiply it by everything. So x times 5x is 5x squared. And these always have to line up. They can't be different degrees. And x times 6 is plus 6x. So 0, negative 5 minus 5 is negative 10. And that's negative 7. Bring down the 5. Repeat x squared into negative 10x squared. This is going to be negative 10. So when I get negative 10 times x squared, and I put it here, I get the same thing because those have to subtract to 0 again. Negative 50x, these seem like big numbers, but it's fine. It's not that big a deal. They'll work out. Negative 60. Do the final subtraction. We're going to be done. Those are 0. Negative 7x plus 50x is 43x. And 5 plus 60 is 65. Then we rewrite. And we usually do it like this. X minus 10. X squared plus 5x plus 6. Plus the remainder. All over what I divided by. That's the division statement from Unit 3. Now, but I'm gonna do a little trick here. Don't worry about it if you didn't do it this way. I don't think it's a big deal for this. You can look back in your note. It's actually a little bit more useful to write it as two separate. It really doesn't matter. The next line is what matters. But these divide to 1. So I get my new graph is x minus 10 plus 43x plus 65 over x squared plus, actually I'm going to write that out factored form. Oh no, I'll do it next. Plus 6. And this is weird, but this is the same as like if you plug this into software, it would graph the same function we're about to graph. This whole thing is the same function as before, which seems strange. But the reason why it works is because if I plug a 2 into this, I'll just get like 8. I'll just get some number, some normal number. And I'll add that to negative 8. Now we get 0 apparently, but so that's obviously not what it works out to. But right, like if I plug numbers close to 0 into this, I'm just going to get regular numbers. The trick is when I plug big negative numbers and big positive numbers, this part gets very close to 0 because this gets really big faster than this. So if I put negative 100 in, this would be very small. So my graph, as it goes out and it settles, it does all this crazy stuff, and then as it gets out into the big X's, it settles into some pattern. It will almost look like this, plus a tiny little bit or minus a tiny little bit, depending on whether this is positive or negative. And that's why this works so nicely for finding the equation of our oblique asymptote, but also testing the behavior around it. So we're going to write this out. Oblique asymptote is y equals x minus 10, where the slope is 1, and the y-intercept is negative 10, and then the x-intercept is going to be 10. And then the remainder part, I like to call it r at x, is this 43 plus 43x plus 65 over, and I'm just going to refactor this. And my testing looks like this. Big values for x, and then we're only going to care if the remainder is positive or negative. This is not true for horizontal asymptotes. Remember we talked previously, but for this it works. So if I put negative 100 up here, that's negative 4,300 plus 65. That's obviously negative. This is obviously negative, and this is obviously negative. So 3 negatives means this is negative. Therefore, we're below the oblique asymptote because it's the oblique asymptote minus a tiny bit. So my function is actually just below the oblique asymptote. And this one is positive, positive, positive. So we're just above the oblique asymptote. Yep.
So it's just the vertical asymptote. What do you have to calculate?
The horizontal asymptote, you need exact values of. Vertical asymptotes, positive, negative is good enough. Oblique asymptotes, positive and negative is good enough. All right, let's get this sketch done. We're falling behind a bit here. Uh-oh. Again, I'm going to start putting in my asymptotes. No horizontal asymptote this time. And I'm going to keep, I've got 2 vertical asymptotes. Again, you should be using a ruler for your asymptotes. And I'm going to keep them nice and close. Usually with oblique asymptotes, it can be tricky to draw if you spread your scale out too much. So I'm going to keep them nice and close. So that's x minus 3. I have some. You should have a ruler. And this is where the trick comes with the oblique asymptote. Actually, I'm going to do the oblique asymptote after. So this is x equals negative 3. This is x equals negative 2. Oops. And I've got, this is almost too close. That's okay. I've got an x-intercept at negative 1. I've got an x-intercept at positive 1. I've got another x-intercept at 5. And I've got a y-intercept at 5, positive 5 over 6. So I've probably gone way too small, but well, it'll be fine once I get it labeled. Finally, my oblique asymptote. Now, my oblique asymptote has a slope of 1, but this doesn't have a scale, so you'll notice it's not to scale. It's not perfect. Like it would be at a 45 degrees if I had a... So this is y equals x minus 10. So that's negative 10, and that's positive 10. Now I'm going to do the same thing, and I'm going to pencil in my end behaviors. As I approach negative 3 from the left, I'm going down. Negative 3 from the right, I'm going up. So here, I got to bring this down a bit further. I'm going down. Here I'm going up. Negative 2 from the left, I'm going up. Negative 2 from the right, going down. Up on that side, down on that side. And finally, my oblique asymptote out to the left, big negative, I'm below, out to the right, I'm above. So here I'm below, and here I'm above. If you want to watch me put all the pieces together, it's not a bad idea. I'm going to zoom in on the different parts. Try to draw a smooth curve. Don't make it do anything wonky that it doesn't have to be doing. So those parts fit, makes sense. It could cross over the oblique asymptote and approach from above. It's possible. It could also include an x-intercept if it did that, but it wouldn't have to, so that gets a bit trickier. This is just a little blip like that. Squeeze it in, that's fine, but make sure it's visible. And here's the most interesting part of this graph. And let's see if I can do it properly. So I'm coming up here, quickly turning, and quickly turning again. No, not quite. Try that again. So once again, your pieces have to fit. Look what happens. It crosses through this x-intercept, crosses through the y-intercept, crosses back through, then crosses back through and approaches from above. Interesting, yep. Very good. What about the hole? So then, usually when you do this, you just got to try to remember if there's a hole, make a mental note, not forget about it, and then you go back and take your eraser, preferably, erase a little part of your graph around where the hole would be. Draw it back in and mark it. So logarithms, these are two equations. One's an exponential that we solve using logarithms. The other is logarithmic that we solve using exponentials, sort of, at least. You know, I feel like this, like they're both a little bit like this, but A is one where you really want to, it's kind of wonky, so you really want to be familiar with the steps. And if you are, it becomes very easy. Every one of these questions is very much the same. And then, I mean, B is kind of the same. You end up factoring. You got to know what to do. But it's a little bit more straightforward once you get the first step right. It kind of falls into place. Whereas A, you really want to be familiar with all the different steps. The first thing we're going to do is take the log of both sides. If it wasn't such a complicated question that had exponents on both sides and numbers multiplied by those exponents or those powers on both sides, you might be able to do log of some base that's helpful. In this case, I don't think so, so we're just going to do log base 10. And this is useful because now I can use one of those properties of the logs that a product in the argument of a log is the same as the sum of the logs. So I can add these separately on both sides. So you got to know how to take the log of both sides. You got to know that you're splitting those products up into sums. And then this huge important property, and I hope you're watching and you remember this. And you could do like at least these 2 steps, if not all 3. You could do them all together as one step, right? But I'm showing extra work right now. Log base 5 plus, logarithms allow me to take this exponent out front, which is in some ways the trick. It's the power of, one of the main powers of logarithms. But there's more. There's still other steps that you kind of need to know what to do. From here, you really just like doing some algebra, expanding, moving things around, doing some factoring to isolate x. But because of the logarithm junk that's in there, it's useful if you're familiar with how the steps work. And the first thing we're going to do is expand those brackets. Then I'm going to move the 2x terms to the same side and everything else to the other side. So I end up with this one, which is x log 2.7, and this one minus 5x log 4.2 equals log 3, whatever's left on this side, minus log of 4.2 minus log of 5 minus 4 log 2.7. Is everybody okay? I'm not going too fast here. Common factor out the x. That's how we isolate it.
It's supposed to be log.
Where did I write that? This is minus. And then I divide by this, and that's how we isolate x. The brackets here. Now you could, if you wanted, depending on your preference, depending on how you like to enter things into your calculator, with log laws, I'm subtracting logs with the same base. So I can put all of their arguments together. So this could be log of 3 divided by 4.2 times 5 times 2.7 to the 4 over log of 2.7 divided by 4.2 to the 5. A little bit easier to put in your calculator. Maybe, I don't know. It totally depends on you. It's like less brackets if you do it this way. And I'm not going to bother punching it in right now. I'm just going to write down the answer. You can check it later. Make sure you can do it. They pretty much always end up being at least this complicated. And so it's a lot to punch into your calculator and get it right. And on the exam, you don't get to check your answer. So you want to be able to do it right the first time. Okay, next one. Any questions about that one? Are we okay? There's sort of 2 different ways you could do this one. It's a minor difference, but some people do have a preference. So I'm going to quickly show them both. Not the whole thing, but just the extra difference in step. So the first thing I'm going to do is recognize that I'm adding logs with the same base, so I can turn them into a product. So I get log base 3 of 2x plus 1 times 5x minus 1 equals 1. And the difference, if you do it the other way, this part's the same, but you want to turn this into log base 3 of something. So log base 3 of what equals 1? 3 to the 1, or 3, yes. So I turned 1 into log base 3 of 3. And then I would have, therefore, this thing equals 3, which is just these brackets, and I go on from there. Otherwise, if you do it this way, you're rewriting in exponential form. And how do we rewrite in exponential form? Well, if it was log base 2 of 8 equals 3, this is a good one to memorize, because 2 to the 3 equals 8. And on your calculator, if you were doing an exam and you forgot exactly how to rewrite a logarithm, because it's useful, obviously, to do this, you should know 2 to the 3 is 8 and just figure it out. You know what I mean? Like, make it work. And on your calculator, this would, if you have the log button, you can do that, or it would be log of 8 over log of 2 equals 3. So you can always go and check to, if you kind of forget the notation, but you can think about it, you can go and check over the notation. And remember, what was the thing that was the most important thing that we learned in logarithms was the base stays the same. So if 3 is my base, how do I rewrite this? 2x plus 1, 5x minus 1 equals the base, which is 3, to the exponent 1. And notice how this is the same as this. And to me, the difference is like nothing. Like, do it one way, do it the other way. It's the same thing, but some people do have a preference. So there you go. And now what do we do? You know what? I don't think we know how to solve this. Oh, this is a grade 10 question now. Expand, simplify, move everything to one side, set it equals 0 and factor. After the whole MHF exam, you get to this question, you go, I don't know how to solve this. Oh, no. Don't fall for that, right? So let's see. That's 5x minus 2x is 3x minus 1 minus 3. And I'm pretty sure this is factorable. And we're done. No, we're not done. What did we forget? What did we forget at the very beginning of the question? What's really important about logarithms? Restrictions. Remember this? 2x plus 1 has to be greater than 0. The argument of a logarithm can't be 0 or negative. It's got to be greater than 0. So x has to be greater than negative 1/2. And 5x minus 1 has to be greater than 0. So x has to be greater than 1/5. And if x has to be greater than negative 1/2 and greater than 1/5, it has to be greater than 1/5. That one's irrelevant. It's got to meet both of those restrictions. Yeah. Which means that one's inadmissible. Yeah, we just take the arguments of the logarithms can't be 0.
So since 1/5 is smaller than
Bigger because it's positive. Look back at this. Logarithm restrictions always work out that way. Almost always. You've got 2, but it boils down to 1.
So like one of them has to be for both of them. So you picked 1/5, so because it was so.
Because if a number has to be bigger than -1/2 and has to be bigger than 1/5, then it really just has to be bigger than 1/5. We only have to think about one of the 2 restrictions. Oh my gosh, we're finally almost done.
Is this the last thing?
Yep.
No more jump scares.
Well, there's the exam that you have to write next week, but
I'm not gonna get you sick.
okay, let's get this done quickly. It's pretty straightforward. Traces of burnt wood were found in an archaeological dig in Chile. The wood was found to contain approximately 1.6% of the original amount of carbon-14. The half-life of carbon-14 is 5,730 years. Approximately when was the wood burnt? Rounded to the nearest year. So if you recall, we use this. You shouldn't have to write this down because you should have it on that handout, right? This is decreasing, so it's 1 minus r to the t over n. Where A is the final amount, A naught is the initial amount, R is the rate that it's increasing or decreasing. In this case, it's half-life. T is time, and N is how long it takes for the increase or decrease to occur. You need to know what they represent, definitely. And memorize that formula, yeah. Half-life is a little bit easier because we know what the multiplier is. So if the final amount is 1.67%, what's the original amount? 100. 100%. That's a little bit of a weird thing. We didn't do an example like this in class, but it was in the review or the practice that day. But it is something that you need to be able to think through. This is a ratio. I could double both sides, triple both sides, halve both sides, and it wouldn't change the question, it turns out. So then this is 1 minus a half, which is just a half to the t over, and 5730. You definitely need to know where that goes. Goes in for n. I divide both sides by 100. Then we rewrite this as a logarithm. Base stays the same. Logarithms solve for the exponent, so the exponent comes out. And that's what I'm solving for. So the exponent equals log base 1/2 of 0.0167. And if you have a calculator that doesn't have the button, that's log of 0.0167 divided by log of 1/2. So log base 10. Change the base to whatever you want, but the whole point, if you're using your calculator, is you want it in base 10, because that's what your calculator does. So then t equals 5730 times log of 0.0167 over log of 1/2. And that works out to apparently 33,830 rounded to the nearest year. Therefore, the burnt wood is approximately 33,830 years old.